Well, thank you all for having me here. My name is Dominic Rizzo. I lead the OpenTitan open source Silicon Root of Trust project. In the past, I've also led our internal security key hardware project. And today what I'm going to talk about is the Silicon Root of Trust technology, what we call our Titan technology, and how it enables authentication from the data center to the user. So what I'm going to talk about is what's a hardware root of trust, or a silicon root of trust, I'll often say, and why do we need it, how we use it throughout our data centers and our products, our devices, how it impacts the users, how it supports user authentication and identity, and how we're going to go about making this technology available to the industry as a whole. And then, of course, we'll open it up for some questions at the end. So let's talk a little bit about why we are interested in root of trust technology at Google. So we have a huge volume of data center equipment. This is really where, when we talk about Titan technology, where it started. We have a planet-wide network, 19 data centers, 5 continents. They power all of our services, search, YouTube, Gmail, what have you. This doesn't even include our 20 regions for our enterprise cloud customers. And all of this really runs on top of physical hardware, physical infrastructure. So servers, network cards, storage devices. And it's mission critical to our success and that of our partners and users that infrastructure be secure, and it be secure from the very lowest layers. So this is a very large attack surface, and it requires state-of-the-art defenses all the way down the stack. And based on these articles, even including in the last few weeks to month or so, where we saw the second low-level UEFI boot firmware attack, persistent firmware attack, we know that these attacks are a realistic and growing concern. So we had to do something about it for our infrastructure, and now we're really moving to a posture where we want to help solve this issue throughout industry. So we need to root our trust all the way down in the silicon, and we need to use that silicon root of trust, that hardware root of trust, to transitively verify the code running in our servers, on our equipment, on our network cards, all the way up through the very top of the stack. So when I say root of trust, what I really mean by that, because it can be a kind of a squishy concept, is the set of inherently trusted functions within a platform. And preferably, we want to root that all the way down in silicon, in a chip, in an IC. So at Google today, in our data centers, we use this Titan silicon as our root of trust. Now, this is an in-house proprietary piece of silicon, and when we say Titan class security, we don't just mean the chip. We actually mean all of the security design principles that go into that. We mean the firmware. We mean the provisioning flow. We mean everything that really surrounds the device. And it's our root of trust technology, right? This started out as a homegrown technology, and now we're looking at moving it out into the rest of the industry as well. So what do we use this Titan technology for in our data centers? Well, it gives us a set of principles or properties, right? We want it to be transparent, trustworthy implementation, so that's why we built it ourselves. It provides us first instruction integrity, which is knowing that the very first level of firmware, the boot firmware, is what we expect it to be, and it's only what we expect it to be. So it provides a trusted machine identity, so it provides a core part of the machine authentication to the rest of the data centers, to our network. It provides some level of physical attack protection, as well as provides some set of services, things like tamper-evident logging. What it looks like in action is the Titan silicon and the firmware and the rest of the infrastructure. It sits between the control hub and a server. This would typically be a BMC. There are other integrations possible, and the system boot flash. And what it does is, as the machine boots, it checks that firmware against a known good manifest, verifies that it's the correct firmware, and if so, it grants it the appropriate cryptographic or security credentials to get onto the network. If not, we actually allow the machine to boot, but we don't grant it the trusted identity. We don't let it authenticate to the network because we want to be able to fix the machine. We want to be able to diagnose the machine, but we don't want it to be trusted. We don't want it to be authenticated. So it's not just for the data center. We actually use this within all of our Chromebooks as well. So the Chromebook line has always had a hardware root of trust, historically a TPM. But starting in 2017, they've actually begun to transition to our Titan C security chip. More recently, the Pixel 3 and future models have moved to the Titan M security chip, which we use to implement a similar set of principles that are rooted in the root of trust. So let's move from our machines, our hardware devices, and talk about how the root of trust protects the user. We know that a huge number of information security attacks, a huge percentage begin with phishing. We know that a huge percentage of attacks on businesses include phishing. And it's important to kind of consider this in a holistic sense of, well, if we know certain characteristics of an attack, that can tell us a likelihood of your account being hijacked. So really, if you look at this set of numbers, you can tell that having been phished is far and away the greatest predictor of account hijacking. So it's a very serious issue, and we take it seriously, and we address it. How do we attack it? How do we address the issue? Well, with second-factor authentication for the user. It's important to understand, though, that not all methods are equal. So we really recommend the use of a hard second-factor authenticator. And of those, we really consider FIDO-compliant security keys, those that implement the U2F or universal second factor, to be best-in-class multi-factor authentication devices. We consider them to be fundamentally phishing resistant. So of these hardware-backed U2F tokens, so security keys, we really consider them to be this best defense. And one example of this strong form of user account protection is Google's Titan security key. Now, it uses an off-the-shelf silicon root of trust because the Titan class silicon wasn't available at the time, but the silicon root of trust firmware runs known good Titan firmware. So built around the same set of principles. So when I say known good, I mean that it's verified in a similar fashion. The firmware is verified in a similar fashion to the data center example I just talked about. So there are a couple of key points here. The Titan security key enables account protection at our highest levels. It is based on trusted hardware, the root of trust, and it's really based around an open ecosystem. And you'll see later in this presentation that open ecosystems are very important to us. Open standards, but also open source ecosystems. So what do we want to achieve with these hard second factors? So what the core issue is that a user is pointed at a phishing URL, and the security key actually tells the website upstream what URL the user is pointed to. If it's correct, it allows login. If it's not, it denies it. Very similar to how we provide those authenticated credentials in the data center. So here's how the technology works. Alice is trying to sign in. The server gives a challenge to a login web page. Web page asks the browser for a security key signature. Now you notice in this step, the browser tells the security key which URL the user is on. So the security key, Alice's security key, signs across this entire bundle, and then that message goes back to the server. Now, the server can see that 1, Alice's key signed this. 2, yes, it was a current challenge, that what we call a nonce was in fact fresh, and that crucially, that Alice was actually pointed to google.com and not elsewhere. Now, this is how hardware-backed phishing-resistant user authentication works. And again, the silicon root of trust provides these core security guarantees. So again, this is also present on our devices. It's not just in the data center, it's not just with the user. We've put this Titan M secure silicon into the Pixel 3 line of phones, and we've created a trusted path to a physical button. And that physical button allows us to provide validated user presence in an unspoofable manner. We've also done this with Chromebooks. The Titan C security chip is present in the Chromebook line, all of the new Chromebooks at this point. So we've integrated the security key functionality as well, but here the trusted path is the power button. It's again provable user presence. So in this manner, we've really taken the Titan root of trust security technology and woven it from the data center through our product offerings and enabled it to support user authentication. Now, this has really been great for Google hardware, Google products, and our users, but how do we make this benefit of a silicon root of trust available across industry and to everyone? And crucially, how do we show that it's trustworthy if we do provide it or when we do provide it? So this is, we do that through the OpenTitan project. And OpenTitan is the world's first transparent, high-quality, open-source reference design for a silicon root of trust. And it's not just driven by Google, but it has an active and vibrant contributor community in the open source as well. Now, it's built on top of what we've learned from the previous line of Titan Silicon, although it is a completely new code base. And you can actually visit the website and go to the GitHub repository for it and see the design in depth today, all the way down into the what we call the RTL, into the hardware design itself. You can, in fact, even download it and run the design on FPGA hardware today. So why did we move to an open implementation? Or why are we moving and developing this open implementation? Well, one, like I said, is you've got to show that it's trustworthy, and that's just not to people using it, but also to ourselves as well when we consume these devices. So openness and transparency enhances trust and security. There's a many eyes aspect to this. So it enables and encourages innovation. We actually have a number of ongoing collaborations and partnerships with academic institutions today. There are papers today that are built around the OpenTitan root of trust as a baseline, and then they've added, security innovations on top of that. And finally, it allows for an equivalence between the design and the specification. So instead of having an open specification that there are multiple implementations to, where sometimes there are different interpretations of what the specification means, we actually provide this open source reference design so those two are equivalent, so that we know what the security properties are because the design has been implemented as specified. So you can see here how OpenTitan differs from a traditional root of trust. What we've done is we've made open everything that can be made open. Now there's a set of blocks that are grayed out, physical design, analog IP, things of that nature, because there is in fact a foundry boundary below which it's not really practical to make things open. So we've really done the limit of what's possible today in terms of making an open design. Now, the project itself is really guided by a few principles. First is transparency. Obviously, like I said, this is a way of building confidence in the design and allowing and enabling others to work with it. The other is quality. It's important to know that a high quality design is often very well aligned with a high security design. So we do enforce via publication of standards in our community review process, pretty rigorous code quality requirements, which also, by the way, makes it useful for others to integrate because it is a high quality design that is available under a permissive open source license. So finally, it's community driven. So it's not just us, it's our partners as well. And we have a number of strategic partners. Now, they include everyone from third-party not-for-profits like the Cambridge UK-based low-risk organization. Now, they're actually responsible for the maintenance and upkeep and standards enforcement for this OpenTitan silicon design. So they are there to act as a community community steward to keep the design up to date, to keep it current, to keep it high quality. We also have academic partners like ETH Zurich. We are building this design around a processor core that was originally developed by them, although we've extended it and added a large amount of testing and verification on top, as well as a number of large commercial partners, Western Digital, Seagate. These are folks that are deeply engaged in the open source silicon community today. Like I mentioned, ETH Zurich, we use one of their RISC-V processor cores. And G&D Mobile Security is really a world leader in certified secure element technology. So, we work closely with them on the physical security aspects of the design. So this is really a community effort to build an open source silicon root of trust. And finally, it's great to have the open source design, but at some point it has to turn into a product. So we are working with Baton to produce the first OpenTitan silicon product, the first discrete chip based on the open source silicon project that we have been incubating and developing over the last few years. What's next for us? Well, we're always recruiting new partners to contribute. We're having conversations with everyone, and we're continuing to develop the design on this path to tape out. We really opened it up about a year ago, last November, to encourage other people to get involved and engaged with the open source project. And finally, we're going to produce this first piece of discrete OpenTitan silicon within not too long now. So in summary, we believe that security belongs in the silicon. It begins in the silicon. We do this with Titan class technology in our data centers, our devices, and our products. We also think that you as a user should be protecting yourself with a silicon root of trust based security key like the Titan key. And we are bringing the silicon root of trust technology that we have developed to the community and the rest of the industry as a whole. Finally, thank you so much for having me. I've really enjoyed presenting on this root of trust technology. And I'm happy to open the floor for questions now.